So as was mentioned in a previous video, okay, complementary angles are angles that add up to 90 degrees or to pi over 2 radians. So this angle B and this angle A are complementary because the angles of a triangle add up to 180. Since I already have 90 taken care of, these must add to 90 degrees. Their complementary is really just a term meaning they belong to the same right triangle. And was pointed out before, okay, the ratio B over C, so here's B on this side and here's C, the hypotenuse. If you're talking about the angle B, that's opposite over hypotenuse. But if you're talking about the angle A, that's adjacent over hypotenuse, which means the sine of B is the cosine of A, and vice versa. The cosine of B is the sine of A, sorry. They both refer to the ratio A over C. Okay. By the way, it's very, very standard when working with triangles to use capital letters for angles and lowercase letters for the side across from that angle. It would be very, very weird to label this angle A and this side A. This would be very confusing to people once they've got some practice. No, the side across from angle A is what you label as letter A. It's just a notational way to keep things straight so that you make fewer mistakes. Across from angles put sides of the same letter, and we tend to use capital letters for angles and lowercase letters for sides. But anyway, this slide just sort of points out this complementary angle business. The sine of B is the cos of A, the secant of B is the cosecant of A, the tangent of B is the cotangent of A, and vice versa, when you have complementary angles A and B, aka two angles that add up to 90 degrees or pi over 2 radians. And that's exactly what we've just said. So let's use that. So how can I use complementary angles? Express each of these in a different way, using a different trigonometric function. So instead of sine of 79, we're going to want cosine of what? Something that makes it add up to 90. So 79 plus what is equal to 90 degrees? I'm assuming that this 79 was not radians, it was supposed to be degrees, because it would be a very unusual radian measure. Well, then x needs to be 90 degrees minus 79 degrees, which is 11 degrees. So the sine of 79 degrees is the cosine of 11 degrees. Now, parts B, C, and D are not in degrees. They're in radians. And then I don't want the complementary angle to add up to 90 degrees. I want it to add up to pi over 2 radians. So for part B, the tangent of pi over 18 is going to be the cotangent of something. And what is it? I know if I add it to pi over 18, I get pi over 2 radians. So complete part B and C and D, and then we'll check our answers. I'm going to erase the work here so that the fancy computer typed text can show up cleanly. But go ahead, stop here and finish. Okay, so for the first one, it's cosine 11, as we just saw. For parts B, C, and D, we need to work in radians, which means we use pi over 2 instead of 90 degrees. So we get cotangent of 4 pi over 9, the sine of pi over 6, and the secant of pi over 12. So if you got all of those, great. If you made some mistakes, check here and see what went wrong. Otherwise, we're going to keep going. So this is now just like a little summary of basic geometry that we should already know. Complementary angles add up to 90 degrees and the Pythagorean theorem. Okay? No big surprise there. So now let's use those bits of information to what's called solve a triangle. And by solve a triangle, it means fill in all of the angles and all of the sides. So I have 2 unknown sides and 1 unknown angle. So can we fill in the rest? So the first thing that leaps out, at least to me, is as soon as you know 2 angles, you know the third. So that third angle must be complementary to 35 degrees, and that's 55 degrees. But how am I going to find the missing side lengths? If I jumped right to the Pythagorean theorem, I'd say a squared plus 4 squared equals c squared, and I have 2 unknowns, and that's not going to help. Okay, so don't jump to the Pythagorean theorem yet. The Pythagorean theorem is only useful when you know 2 sides and need to find the third. Okay. So how are we going to find one side? Start using some trigonometry. Okay. So for example, there are a lot of options here. You could do the tangent of 35 degrees is opposite a over adjacent 4. Tan 35 is a over 4. You could also say the cosine of 35 is adjacent 4 over hypotenuse c. You could use complementary angles. You could say the sine of 55 degrees is 4 over c, because it's complementary to 35. Okay, so there's not like one unique way to proceed from here. The way the book has chosen to do it is using these. So if I solve for a and c, we get a is 4 times the tangent of 35 degrees, approximately 2.8. By the way, on an exam, remember you are never required to use a calculator. If you simply write 4 times the tangent of 35 degrees, you get full credit. That is perfect. You can stop there. Okay, and if all you did was none of this work was shown and all you said was this, you just drew this stuff in here, I'm going to presume you either copied it off someone else or you have a stored program on your calculator that does this and you don't know how to do it yourself. Either way, you get 0 credit. Okay, if all you've done is write down a decimal approximation with no supporting work, you get no credit, which basically says you need to show this work anyway. So you've already figured out that this side is 4 times the tangent of 35, and I'm telling you that's where you can stop. If you punch this into a calculator and get an approximation, you're only risking that you mixed up degree mode and radian mode, or you accidentally entered 350 instead of 35, and you make a mistake and you start losing points. At 4 times the tangent of 35 degrees, you are done. Full stop, 100% credit, leave it there. Similarly, c is 4 over the cosine of 35 degrees, which you could also write, of course, as 4 times the secant of 35 degrees. Either one of these would be complete credit. 4.88, sure, if you want a decimal approximation, you can do that. But notice we've now solved for the right triangle. Okay. It's not the only way we could have done it. Let's suppose we've solved for a. A is 4 times the tangent of 35 degrees, but we still don't know what c is. Then we could use the Pythagorean theorem. Okay. So up at the top, a squared plus 4 squared equals c squared. We just got a is tangent of 35 degrees. I can factor a 4 out. And what's left behind is tan squared of 35 degrees plus 1 equals c squared. Hey, tan squared plus 1, that's equal to secant squared. So 4 squared secant squared of 35 degrees equals c squared. And if I take a square root, we get that c is 4 times the secant of 35 degrees, plus or minus, but since we're dealing with lengths of a triangle, it's definitely the positive one. So we could have also done the Pythagorean theorem to get this missing side length. Again, lots of options here. Okay, let's do it again. We are given 2 sides, but only 1 angle. Can you fill in the missing things? Well, okay, when you have 2 angles of a triangle, then you use complementary angles to get the third. If you have 2 sides, you can always use the Pythagorean theorem. Notice this is all in a right triangle. In later sections, we're going to talk about triangles that are not right triangles, in which case you don't have complementary angles and you don't have the Pythagorean theorem. But in right triangles, if you have 2 angles, get the third easily. If you have 2 sides, use the Pythagorean theorem to get the third side quite easily. And then you'll have more information, and then you can rely on trigonometry. So in a right triangle, whatever you have 2 of, the third one you can get pretty quickly. So in this example, we have 2 sides, 2 and 4, so we set up the Pythagorean theorem to get that the missing side is 2 times root 5. It's just worked out right there. So now that we know, and again, just call it 2 root 5. You don't have to write it as 4.47. So now we know that this hypotenuse is of length 4.47. And now we can start using trigonometry to fill in the missing bits. So for angle A, the tangent of A is opposite over adjacent, which would just be 2, which makes A the arctangent of 2. And you can leave it in that form, or if you want, you can use a calculator mode. If you want to work in degrees, that's okay. Just make sure, again, if you're working in radians mode, that's great. If you're working in degrees mode, that's fine. But make sure to say your answer is in degrees. If you wrote A is 63.4, I'd probably take off a point out of spite, okay? Because this is implying you're working in radians. It's not 63.4 radians, it's 63.4 degrees. So if you're working in degrees, use degrees, sorry. And then once I know two angles, use complementary angles to get the other one is 26.6 degrees. I would do this actually a slightly different way. Okay, so I'm going to erase this so we have a little bit more blank space. It starts off the same. You really need to start off with C is 2 root 5. That's how you find the missing side. Okay. But now, remember, this reference triangle I drew in a previous video. If you have a right triangle and a theta, and this is the radius, this length is definitely r sine theta, and this length is definitely r cos theta. And in our triangle over there, that tells me that 2 must be r times the sine of b. Similarly, 4 must be r times the sine of a. Okay, alternately, you could say 4 is r times the cosine of b, and you could also say that 2 is r times the cosine of a, depending on whether you're making this your reference or you're making this your reference angle. And we know r, it's 2 root 5, okay? So let's just proceed with 2 is r sine b. So 2 is 2 root 5 sine b. Cancel off the 2's and divide by root 5. So the sine of b is 1 over root 5, which you can simplify if you want to root 5 over 5, which means b is the arcsine of root 5 over 5. There we have it. They had arctangent of 1/2, I guess, for b. Actually, I think they said arctangent of 2 for a, and then used complementary angles. But you could have also called it arcsine of root 5 over 5 for b, and you could do similar work to end up with the angle a. And if you punch this into a calculator and get an approximation, fine. Just make sure you're clear about whether you're doing radians or degrees. But you can also just leave it like this. This is 100% correct. You're golden. That is an angle, and you're fine. Now, when working with arcsine, you have to be a little careful. I'm not going to erase everything. I'm just going to erase that last bit. Okay. So we had these 4 expressions here that could all be used to find a and b. So an instinct that you start to develop when you've done this a while is you just sort of ask yourself, would I rather work with sines or would I rather work with cosines? Because in this problem, what we're going to have to do is take inverse trig functions. And always remember that the range of arcsine is negative pi over 2 to pi over 2, but the range of arc cosine is 0 to pi. Now, in these sorts of problems, we're dealing with angles in triangles. They are first quadrant angles, so either one of these is fine. Okay, we don't have any negative values, so it doesn't really matter whether I have a quadrant 4, which would be a negative height, a negative sine, or quadrant 2, which would be a negative width or a negative cosine. Because we are in actual triangles, everything's positive. We're in quadrant 1. It won't matter whether you use arcsine or arc cosine. But sometimes in other problems, you'll have a choice. Would I rather solve for b using sine or cosine? Well, it's going to depend. Do I already know what quadrant it's in? If you already know it's in quadrant 2, you definitely want to use the cosine, because the arc cosine is going to give you the correct angle. Arc sine would spit out something in quadrant 4. It won't be the same thing. Okay, similarly, if you happen to know, if you're trying to solve for a, and you happen to know that a is a quadrant 4 angle, which wouldn't happen in this problem, okay, but maybe in another problem. If you know you're looking for a quadrant 4 angle, then arc sine is going to be the correct thing to use, because arc cosine is going to be ambiguous. It's going to spit out something in the wrong quadrant. So you have a choice between sines or cosines. In quadrant 1, it won't matter. In other quadrants, it might, so just be careful about that. Okay, so this is all the work we already saw. All right, so let's keep going. So you might observe we skipped example 6. There was an error in the PowerPoint slide. Not like they made a mistake. I mean like an actual error that the document could not correctly read it. Anyway, so we start from a hotel. It's at an elevation of 8,000 feet. So here's where we start, 8,000 feet up. And then we want to go up to an 11,100 foot overlook. The trail is 14.1 thousand feet long, close to 3 miles. Okay. So what is the average inclination, the average grade of the trail? So when you're like writing map guides or something, you really want to know what the steepness of the trail is so that you can indicate how difficult it is. So we go up 3,100 feet because we went from 8,000 to 11,100. And the trail length is the hypotenuse of this triangle, and it's 14,100 feet long. So we now need to solve what's this angle B. So we're going to use triangles and trigonometry. Okay. So specifically, if I redraw that figure, we know that this angle B is the unknown. We know the height is the change in elevation, which was 3,100 feet, and we know the trail length was 14,100. So between this hypotenuse and the side opposite it, we want to use sine. If we had known this length down here, we'd use cosine. If we knew these two and didn't know the hypotenuse, we'd use tangent. Always use the appropriate trig function to the information you have. So since we know the opposite height and we know the hypotenuse length, we're going to use sine. We happen to know this is a quadrant 1 angle. Therefore, arcsine will return the correct value. Okay, and we just take the arcsine and end up at 12.7 degrees, or whatever the appropriate quantity in radians is. If this were an exam, you could leave it like this. Again, anytime you're working on an exam and you think, I don't have a calculator, so I can't go any further, that's not true. You never have to have a calculator on an exam. This is already completely correct. So the average inclination is about 12.7 degrees. That's pretty steep, to be honest. Okay, so that's where we'll stop for this video. So come back in the next one, and we're just going to keep doing examples. I just don't want the videos to get too long.